A Chronicle of Discovery. The Evolution of Thermodynamics and Quantum Mechanics. The history of modern physics is the story of two revolutionary ideas that reshaped our understanding of the universe. This narrative traces the evolution of these twin pillars, thermodynamics and quantum mechanics, from their classical roots in the mechanical, clockwork universe of thinkers like Isaac Newton to their modern synthesis by scientists such as Richard Feynman. It is a chronicle of a profound intellectual journey, one that forced science to abandon a world of deterministic certainty and embrace a reality governed by probability, statistics, and the fundamentally strange rules of the quantum realm. The Clockwork Universe. Foundations of Classical Physics. Before the revolutions in thermodynamics and quantum mechanics could unfold, a stable and powerful intellectual framework had to be established. For over 2 centuries, physics was dominated by a deterministic worldview, a clockwork universe largely designed and articulated by Isaac Newton. Understanding this classical foundation, a world of predictable forces, absolute time, and unwavering causality is essential to fully appreciate the radical and counterintuitive nature of the scientific upheavals that followed. The Newtonian worldview, in his monumental 1687 work, Philosophiae Naturalis Principia Mathematica, Isaac Newton laid out the mathematical principles of natural philosophy that would define an era. He formulated the laws of motion and the concept of universal gravitation, providing a unified explanation for both the falling of an apple and the orbit of the planets. His work suggested a universe that operated according to precise, discoverable laws, one that could be understood and predicted through rigorous observation and calculation. Crucially, Newton also refined the scientific method. He insisted on grounding explanations in observable data rather than speculative reasoning. This emphasis on empirical deduction is famously captured in his phrase, hypotheses non fingo. I frame no hypotheses. By this, Newton declared that for a proposition not deduced from the phenomena, it is to be called an hypothesis. And hypotheses, have no place in experimental philosophy. For Newton, a hypothesis was a speculative cause, not directly inferred from observation, and he believed such invention undermined the integrity of his rigorous experimental philosophy. The nature of light. While Newton's mechanics were ascendant, a debate simmered over the fundamental nature of light. Newton himself, in his work Optics, favored a particle theory. However, an alternative wave theory, championed by Christian Huygens, also persisted. The pivotal moment in this debate arrived when Thomas Young presented his findings to the Royal Society in 1803 and published his classic paper, Experiments and Calculations Relative to Physical Optics. In 1804, by shining light through 2 thin slits, Young observed a pattern of bright and dark bands on a screen behind them. This interference pattern was a hallmark of wave behavior, where overlapping waves either reinforce or cancel each other out. Young's double-slit experiment provided powerful, direct evidence that light behaved as a wave. With the mechanical and optical foundations established, a new science of heat and energy began to emerge, driven not by abstract philosophy but by the practical demands of a new industrial age, the age of steam. The field of thermodynamics did not arise from pure theoretical inquiry but from the gritty, practical challenges of the Industrial Revolution. Its principles were discovered and codified in the quest to understand and improve the efficiency of the steam engines that were beginning to power the modern world, transforming industry, transportation, and society itself. From engines to principles. The story begins with the early, often inefficient, inventions designed to pump water from flooded mines. The miner's friend, invented by Thomas Savery in 1698, and Thomas Newcomen's fire engine of 1712 were crucial first steps. However, it was the Scottish engineer James Watt who made the critical breakthrough. In 1764, while repairing a model Newcomen engine, Watt recognized its profound inefficiency. The design wasted enormous energy by repeatedly heating and cooling the same cylinder. His solution, a separate condenser, dramatically improved fuel efficiency and highlighted the central importance of energy conversion, paving the way for a formal science of heat, codifying the laws of gases and heat. Concurrent with these engineering marvels, scientists were conducting experiments that established the fundamental laws governing gases. In 1662, Robert Boyle discovered that a gas's pressure and volume are inversely related. PV equals constant. In 1787, Jacques Cha found a direct relationship between a gas's volume and its temperature. Joseph Gay-Lussac combined these findings in 1802, leading toward a unified gas law. This work culminated in the modern formulation of the ideal gas law, PV equals NKBT. This equation was a profound synthesis, with Boltzmann's constant kilobyte serving as the crucial bridge, linking the macroscopic properties of a gas pressure and volume to the microscopic world of individual atoms and their energy. Meanwhile, Count Rumford's 1798 work, which demonstrated that heat could be generated indefinitely from friction, began to refute the prevailing caloric theory that treated heat as a fluid. The fundamental laws of thermodynamics by the mid-19th century, these disparate insights were synthesized into universal laws. Hermann von Helmholtz contributed to the formulation of the first law, the principle of the conservation of energy. Then, in 1850, German physicist Rudolf Clausius articulated the second law of thermodynamics. This was not a mechanical law, but a statistical one, dictating that in any energy exchange, the overall disorder or entropy of the universe tends to increase. It established a fundamental directionality to time and placed a hard limit on efficiency, stating that it is impossible to convert thermal energy into other forms of energy with 100% efficiency. Heat, as a rule, flows from hot to cold, not the other way around. These macroscopic laws of thermodynamics marked a major step. But the next great synthesis of classical physics would come from unifying the forces of electricity and magnetism.